This will be an example of how to factor completely. I notice it's not just a quadratic, it has a b to the third. The first thing I would look to do is try to, I've set it equal to 0. I would try to factor the greatest common monomial factor of all terms, and I see that nothing comes out of all of them. B's come out of the first 3, 4 comes out of the first 2, and 9 comes out of the back 2. When I see that, I think, well, I can't take out something out of everything, so I'm going to factor these first 2 and the back 2. So I look at the first 2 and I can see that I can take out a 4b squared. When I take out a 4b squared, I'm left with a b plus 3. Out of the back 2, I can take out a negative 9. Take out a negative 9, I'm left with a b plus 3. When I see that, I can take a b plus 3 out of both those. If I take out a b plus 3, I'm left with a 4b squared minus 9 equals 0. And some people will think, well, we're done. But I look at this one, and that has a special look to it. That's what we call that difference of squares. In other words, the first term, 4b squared, is a perfect square, and the back term, 9, is a perfect square, and I have a minus in between. That means it can be factored further. So I still have this b plus 3. And then I remember my pattern is that I can take the square root of the first, so the square root of 4b squared is 2b. The square root of the last is 3. Make one of them positive, and make one that's identical but with a minus. Oops. A minus. So I have 2b plus 3 and 2b minus 3. Still equal to 0. At that point I can't factor it any further, but I can solve. So either b plus 3 equals 0, which would get me an answer of negative 3 when I solve, or 2b plus 3 equals 0, which would get me, when I subtract 3 and divide by 2, would get me negative 3 halves as my 0, or 2b minus 3 equals 0. So now I would add 3 and divide by 2, and I would get 3 halves. So those are my 3 possible zeros.